Okay, so my talk is called A Brief History of Artificial Intelligence. Brief because I have only 45 minutes. And it is going to be a little bit tainted by my own experience. As you can imagine, since this is my lecture, I can talk whatever I want. So first, let's talk about what is actually intelligence. And there's a lot of people who use that word rather carelessly. And my first exposure, even before I was a university student, was this program called ELIZA. I don't know how many of you have heard about that, but this was very popular in the media. And it really fascinated me because you could have a chatbot that you could talk to, and it would give sort of sensible answers. And people actually had a conversation with that and thought that they were talking to a human. It's called the ELIZA effect because this program was actually really, really simple. But the fact that you have this chatbot which takes the initiative and can decide what it says, actually, it makes it look a lot more intelligent than it actually is. But I was impressed by this kind of thing, and I thought, well, that would be interesting to do. There were also learning machines at the time. That was another direction. So there was this guy here, Arthur Samuel, who used IBM mainframes and implemented programs that could play the game of checkers and could actually learn to beat the best checkers champion that he knew. At the time, this wasn't really a discipline with world champions. So that was another thing that I knew about. And so then my own experience actually wasn't all that different. So I studied at ETH, and at ETH we had Niklas Wirth. And Niklas Wirth said AI stands for astrology, the informatics. So, kind of a very non-serious subject. So definitely ETH was not very interested in AI at that time. And my own experience was in a project where I was doing pattern recognition, or what you would call machine learning today. And I got a whole lot of these kind of nerve spikes. These were from real neurons. And they had to be classified into two kinds. And I had no idea which was one or the other. But the program was supposed to learn how to distinguish them. And it did it to some degree. And I did that with perceptrons, what you call neural nets today, or artificial neurons. And the thing that I retain is that it used an enormous amount of computation, which I could do because I had a side job as a system programmer in the ETH Computer Center. And you see a picture there. So it's pretty similar to the previous guy. I also had big mainframe computers to work on. And the weekends, when we had to fix things on the system, then you could run things on there without bothering anybody. So I ran these big simulations of neural net training. It didn't really go all that far. So I retained from that this impression that that's not really something that I wanted to do. Anyway, whoop. Yeah. Here it goes. So after I finished in Zurich, I wanted to go and do my PhD in AI, but I wanted to do real things, not these perceptrons. And so I studied with this guy, David Waltz, who in fact had figured out how to understand line drawings. So understanding line drawings, you have to kind of classify the different lines you see as edges. They could be convex, concave, or they could be occluding edges on the side. And he figured out how you could actually find a consistent labeling, because all these images you can see, they can flip, like you can see something from above or from below, or different angles if you try hard. And he could actually show what interpretations were possible and which ones were consistent. I could also show that the one on the right was inconsistent. And so that was a technique used called constraint satisfaction, which we actually used a lot later on in my career. Now, a couple of months after I arrived, he left to found a company called Thinking Machines with Marvin Minsky. And so I had to work with somebody else. And the person I worked with was this guy, Jerry DeYoung. And Jerry DeYoung had worked on a slightly different topic, which is natural language processing. And in fact, what he had developed before were programs that could understand stories. So if you look at this story, you read this story, the interesting thing is if I ask you this question, what is Goldstein's, for example, you can answer that question. right? And you can answer all these questions, in fact, but that information is nowhere in the story. So it's impossible to get that information from the story. And the theory is, well, you actually have so much background knowledge, and what happens is that the understanding that you have of the world actually relates it to all these memories. And you know what it's like going to a restaurant and who does things in a restaurant and so on. And so it was really understanding based on a large amount of knowledge. You really had to have a lot of knowledge of what happens in the world and to be able to understand it the way humans understand it. So I worked with him, and actually we started to work with him on machine learning, and a very different kind of machine learning than what I did when I was a student at ETH. It was not the statistical learning with a relatively dumb neuron, but it was an explanation-based model in which, in fact, you would understand the examples that you get in terms of the knowledge that you already had, and so you could learn from a single example. And that's very important for the survival of humanity. For example, if you wanted to learn how not to fall off a ladder, you don't want to have to see 100 examples of people falling off a ladder before you can actually get this. But thanks to this kind of explanation-based learning, observing this just a single time is enough to understand that you have to make sure you kind of support the center of gravity properly. And we had actually, it was my first big conference paper at ICHCA 1985 with Jerry. And so today, actually, large language models can do this. It's called one-shot learning. So this technique actually has come back. And you would see, in fact, that I think today we have come back a lot to this kind of period of the 1980s where we had knowledge-based systems. Oops, what happened now? Now I pushed one button too many. OK, let's see. I think I'd rather go. OK, at the time, in the 1980s, AI was actually really popular. So there was a huge boom. This ICHCA conference in 1985, where I had my first paper, had 5,000 participants. And at the time, that was like the biggest conference ever. So why was that? Well, we had a lot of real successes. So the first group was expert systems. So there were systems like Dendrol, for example, that interprets mass spectroscopy images. There was Mycin that could diagnose infectious diseases and suggest treatments. There was a program called Prospector for finding minerals to tell you where you should dig. And all these were very successful in practice. And also, there was planning. So there was a program called First Nonlinear Planner, which enabled the US military to actually schedule the operations of aircraft carriers much, much better than they could before. There were space missions. They all had to be scheduled with AI. And there were simple robots, like this Shaky, the robot that also could operate autonomously. So we had some real successes. And in fact, a lot of it was for the US military. But it really paid. It was not a promise in the future, but these were things that really worked. And so if you look at this, what I want to point out is that a lot of these applications, like planning and so on, they actually appeal to higher cognitive levels. So there's this Bloom taxonomy that I found out since I'm a professor at EPFL, and we have people who teach us about to classify what we are teaching in terms of this kind of hierarchy. And so there's this lowest level where you just recognize and recall facts. That's sort of databases. And maybe so this machine learning is sort of the understand to some extent. But then the apply, that's sort of expert systems. And the things that go further up, planning and so on, involves sometimes also analysis. And so we were really aiming for these higher levels of intelligence and not just some very simple things that you would hardly call intelligent. Now, what was I doing in there? Well, I worked on something called model-based reasoning. So I didn't really like this machine learning that much. And so this was an approach in which we were deriving knowledge from first principles. like in physics. And so since you don't have numbers, you only have sort of qualitative expressions, then you can only do an envisionment of what could potentially happen given the right numbers. And this is called qualitative reasoning. And this is something that you can really use to have these higher levels of the cognitive hierarchy. So you can do the analysis of something, you can evaluate whether it's good or not, whether it could potentially solve your problem or not. And it can also be used to create new things, as we have shown later on in our work here. My own PhD thesis was about analyzing behavior of mechanisms. Maybe that got me the job here because of the clock escapement things. And so there, I had to basically process just an image. So it was just an image, and only from that, I could tell what are the states this can go through qualitatively, and derive finally that this would function as an escapement. And I could do it for a bunch of other mechanisms. So this is sort of my background on what I think is intelligence. I think intelligence is these higher level functions. That's the part that's interesting, and not necessarily sort of lower level, just predicting something on a bunch of data. Now, what is artificial intelligence? So we do a lot of things. We use a lot of artificial things. We're in an engineering school here. And so clearly, inventing the wheel is something that we don't find in nature otherwise. It's something that we invented. And it lets us go faster. It doesn't solve all the problems for us, but it lets us go faster. And in the same way, in AI, we also have techniques that are different from these basic neural things that people use. So you will generally solve problems by chaining inference, a bit like a large language model. So you chain inference one after the other. This was the theory established by Newell and Simon. And expert systems were pretty close to that. So Mycin was an example. And the way Mycin went over sort of enlarged human capabilities is because it just had so much knowledge. It had over 10,000 rules for infections. So it's more knowledge than any human doctor had. And so its performance was also much better than any human doctor. And so that's one way in which artificial intelligence can go beyond human capabilities. But there are also techniques analogous to the wheel in which AI can work in different ways, in ways that people cannot do with this chaining inference. One example is theorem proving by resolution. So you have this example up here. So I don't think anybody could use a chain of thought to actually prove that these two expressions would imply that B implies A. But a resolution can prove this in just 2 steps. So there is actually a way that we can do things that is more powerful and that is not chaining. And another example is constraint satisfaction. So if you have to solve a kind of puzzle here to schedule, the student has to schedule 4 courses in 3 semesters with these constraints. This can be solved very quickly with constraint satisfaction, but again, it cannot be solved by chaining. You would have to make a lot of hypotheses and come back to them and so on. Very laborious to do. So AI has techniques that go beyond this kind of chaining, go beyond what people normally do, and that's really the value that it had in the 1980s as well. And so when I arrived here, we started to do lots of interesting things. So one of them is design. That's sort of really at the top of this hierarchy. And we worked with architects. We worked on inventing new mechanisms. And Sun Kuhn is here, by the way. So we actually showed how we could come up with a new mechanism design that wasn't known before. In fact, the best design that was known had like 5 parts. And we could do something with 2 parts. So definitely, we could do design with these model-based techniques. Somehow I always have this problem. I think it's, I should probably better go from here. And the technique that we were using for many of these things is, again, constraint satisfaction. And at the time, there was like a big division between constraint satisfaction with continuous numbers, or continuous variables, and with discrete variables. And we actually showed how to combine the two. This was Esther Geller's work, who is somewhere here as well. And that was actually quite useful, for example, in designing bridges. Ian Smith is very familiar with that. And so you have to choose, first of all, what kind of bridge you have, and then you have to figure out the details, and does it actually work with the numbers? And so there's an interplay between the two together that we could actually automate to help people do this kind of design. And so it was not only in design of bridges, but also in configuration, in planning, and so on, that we used these techniques. We also branched into a somewhat different way of looking at something, which is this kind of interactive AI. The starting point was that I was taking the plane and I was sat next to somebody who told me that she was responsible for scheduling all the nurses at the CHUV hospital here. And I said, oh, great, we can give you a system for doing that. They are nice systems. She said, yeah, but we could never use that. And I asked the reason, and she said, well, because it really depends on who can work with whom. There are these people who don't like each other, and if we put them on a team, it's going to be a disaster for the patient. So we all know these things, but we could never write them down. It's very sensitive information, so we couldn't write it down. So then I asked, well, what could you do? Well, maybe the computer could sort of prepare things for us, make us understand, so we can, in the end, pick the right solution. But we can take into account these constraints. And so we kind of developed this into this general abstraction technique, in which we'll say, well, the AI can generate just abstractions of the problem that make it easy for people to solve it. And here's an example for network routing. So if you have a communication network, the question is, how do you route some demand? So it has to go through a sequence of links. And you want to make sure that you can route these things as effectively as possible, given that they come one after the other. And so you can create this structure, which originally we called blocking islands, in which you can sort of tell apart which areas are very heavily connected, where do you have a lot of capacity, and which are the links that have a very weak capacity. So here, there are 3 links with very weak capacity that link this left and this right part. And so if I have to route something between the left and the right part, I have to be really careful which one of these links I'm using, because that's going to break them apart eventually completely. And so this kind of structure becomes a tree. And in fact, humans could solve the problems in there. But also, if you use an algorithm, we showed that we could get a lot more capacity, something like 60% more capacity out of a routing with respect to the state-of-the-art sort of shortest path routing that was around. And so we built actually a tool for that as well. And also a project we did with Swissair on aircraft assignment called SAREX used also similar abstraction techniques. Somehow this really doesn't work very well, but I'll just stay closer here. And so that time we actually had quite a bit of practical impact with model-based reasoning and these kind of abstraction techniques. So this SAREX system was sold to a bunch of other airlines as well. We had application of using AI for regulating traffic and using models of what are good and what are bad traffic situations in order to do this more effectively. It was an interesting work with some people in California. We did this network routing tool, which actually helped to route, to exploit communication networks much better. And people wrote kind of surveys about our lab. So we were quite successful with this work. Another thing we branched into with the HCI group and Prof here is again taking a little bit this idea that we need to somehow interact with humans more directly in order to understand what they want. And this one was not so much about sensitive data, but it was more about people not being able to say what they want. People have preferences, but they can't actually state them up front. And if you ask them to state them up front, they will state far too many. They will state all kinds of things that are actually not that relevant to them. And it'll make it very hard to find a good solution. So we had this technique where you show them potential solutions, and they can express what they don't like about them. And that is used then to make a news cycle and to update these preferences. So we had an evaluation with an apartment search tool. Like we could, students have to all find housing. And there's like a database of 200 apartments. And so you can, of course, go through the whole list. And that's a lot of work, but you could use our tool. And so we had students try this. And so one is, you state your preferences up front. On average, they stated 7.5 preferences, and they had a 25% success rate of finding the best apartment in that list. When we did this in incremental process, they stated only 5.3 preferences, but had a 45% success rate. And there's another technique for adding suggestions, like trying to suggest to them, would you also want to look at this, and so on. That one actually raised the success rate further up to 88%. And so that was also a very interesting kind of work, this user interaction, and actually realizing that people often don't know what they want. We used this same idea in a software architecture which we called smart clients. That was something different from what smart clients, the word was used for other things afterwards. But the idea was that if you did this example critiquing, it would be very heavy on servers. This was in the late 90s, so e-commerce things were not that fast. And so you wanted to run these things on the user's computer. And so we had this tool for planning travel, where you could sort of look for the best flights that you might want to take to go somewhere. And you could specify constraints on when you want to go and what airline you want and where you want to transit and so on. And we kind of, with the constraint programming technique, we could actually compress all this like a little program, an applet that would do this with a graphical interface in the space of about 3.5 web pages of the Travelocity, which was sort of the most common engine at the time. And we commercialized this actually, so there was startup venture funding and so on. In the end, the technology of this kind of farming out the computation to the user's computer became a casualty of virus concerns and also the Java wars. Before the Java wars, most machines had Java installed, and then the Java war was Microsoft no longer installs Java and made it very complicated. Then it was really impossible to run this on people's computer. So it was an interesting idea, and it did catch a lot of attention. Okay, where are we with time? Okay, I think I'm fine. Okay, third topic. This really came up in the late 1990s, early 2000s. We had the internet, computers were connected, they could actually do things somewhere else, right? And so we were kind of interested now in, well, can AI do something in the real world? Not just these tools that tell people what to do or what's the best solution, but can we make them act in the real world? And so the question is, what is the kind of model for agents? And we adopted this model of rational agents. My line was always, well, algorithms always do the same thing. That's the whole point of algorithms, whereas agents do the right thing, right? And doing the right thing means it optimizes depending on the goals and the context that you currently have. And so choosing how to act is a kind of optimization problem, and that brings out the constraint satisfaction expertise that we had into this same space. And so one thing that we worked on was aircraft slot allocation. Oh, interesting, this appears gradually. This is something we did together with Matthias Finger. And so this was a project where we learned a real lot, which in the end didn't have a practical impact because the airlines didn't like it. But the idea is that busy airports, they need to allocate these takeoff and landing slots because you can't have infinite numbers of planes all coming at the same time. And so there's a negotiation that happens. And in fact, this Air Transport Association, which has a headquarters in Geneva, twice a year they hold a huge conference with also about 5,000 people that basically discuss whether they could get this slot and that slot and so on. And this all has to be coordinated, right? Because the plane that takes off in Geneva at 10, it has to have a slot to land in London at 11:15, and not at 3 in the afternoon and not at 9 in the morning. And so this coordination is a huge problem, right? And this was happening with some really backward techniques, so, people meeting each other in the hallways and so on. And so we said, well, we could build a multi-agent systems, right? We could have every airline and every airport represented by an agent, and they can negotiate, and they can find the best solution and cooperate through auctions. And this really taught us the value of privacy. And we developed a whole lot of algorithms that were protecting privacy, because what the airlines worried about the most is other airlines finding out about the routes they were planning to fly. So they did not want anybody to know that they were asking for a slot at this and that airport. This was very sensitive information. But the value, that didn't really matter so much. They didn't think that was very secret. And so we developed this concept of having a distributed system where everybody has their agent, and these agents only find out anything that concerns them directly, but they don't find out about what other agents are talking about. And so this allowed, in fact, to have this guarantee that agents don't find out about competitors. The problem is that the inefficient process we have now, it benefits the large airlines, and they control this IATA organization. So at some point, we got a call and said, well, we asked our board of governors, and they said to stop this work. So that was it. But we learned a lot about the practical concerns and what it would take. And I think these kind of things will still come up. It's not something that's lost. Okay. Another thing when you have multiple agents is that they don't necessarily do what they should be doing. They will be doing whatever is in their own interest. And so these goals that they have, they may actually be in conflict. They may not be all interested in doing everything for the common good, but they will be doing whatever is best for them. And so that leads to the use of game theory. Instead of choosing the optimal actions, we choose actions according to some equilibrium, such that if the other agents don't change, then you also don't have any incentive to change. So it's always optimal locally. And you can influence these equilibria through different mechanisms. So we worked on reputation mechanisms. We worked on taxes that can be raised. And with David Parks, for example, we developed this MDPOP algorithm that reuses a lot of the computation. The computation overhead of these schemes is one big obstacle in practice. And this is also something that we could have used really in this slot allocation project. Another application of agents was kind of interesting was network routing. So we had this abstraction technique, and then the idea was, well, could we have some agents that basically take care of this routing in a distributed way, that build these abstractions, maintain them, and run it in a distributed way. And there's really a tension here because the world changes. So new demands are being routed. The network load changes all the time. And so at some point, you have to decide you're going to make a decision based on this current snapshot. And then you can take the time to propagate, maybe. And so there was a real tension between the two, because it turned out in the end that since you had to wait too long to actually have the accurate information, then taking the optimal decision based on that didn't actually give you a better solution anymore, because the world had already moved on. And so that was a difficult, it was an interesting observation, because you would have thought, oh, this is easy to do, but actually it turned out to be quite difficult. But this kind of smart infrastructure, we kept working on that. So these distributed algorithms, we developed various versions also that could be applied to configuring electricity grids. And so people looked at smart grids with renewable energy. This was already, now 2008, so this is like 17 years ago. We already had the technique. Today, they still don't know how to do this, or at least they claim they don't know how to do this. So there are quite a lot of things one can do. We worked on resource sharing, and there you need some kind of anti-coordination. So if you wanted to route cars, for example, to parking spots, then you should not send all the cars to the same spot. You need to give everybody their own spot, and it always has to be different. So we call this kind of anti-coordination, and it's really the thing that's a little bit difficult in here. And you talked about Stoic. So this is some problem that actually I had been working on and worried about for a really long time, because these things, they have to run in constant time. You cannot go and tell people, okay, you have to wait now. We're going to run this algorithm, and then we're going to tell you where you find your parking spot. But we need something that converges instantly, basically, or at least in constant time. And in fact, we did finally get this. So 2019, we finally got that solution. And we have an algorithm that can do this kind of parking spot scheduling, that can do this network reconfiguration, that can do meeting scheduling, and it can do it, at least in expectation, in constant time. And so I'm very proud of that, finally getting this, although AI has kind of moved on and people don't care so much anymore about smart infrastructure. But I think it'll come back, and I was very happy that before my career ends, we achieved this milestone in the end. Okay, now, these were all the good things we were doing, and we were having a lot of fun. But at the same time, AI was going through this AI winter. A lot of people talk about this. And this AI winter really came about because these knowledge-based systems were expensive to construct. Like it took, you needed PhD level computer scientists to build these. And I remember once I was talking to people at IBM, and they said, well, we have only 100 of these educated every year in the United States, and we would need 1,000 of them to roll out this technology to all our customers, so we can't do that, right? And so there were sort of these diminishing expectations to say, well, we can build these great systems, but the cost is too high, it's difficult to maintain them, and so on. So we reached this diminishing expectations. And what it meant is basically machine learning, so rather than having knowledge and building systems with a higher level of intelligence, we're basically doing much more simple things. And this was fueled also by the fact that we had suddenly an abundance of data through digitalization. And so it was possible to use these, basically, I would call them pattern recognition, things like for detecting digits, for computer vision, recognizing things in images, and so on. Preventive maintenance, by the way, that's something we worked on at Swissair in the early 1990s already. So all these things, they use very simple techniques. There's no higher level cognitive skills. It's basically only just recognizing patterns in the data, being able to make predictions, and focuses on some kind of statistics and black boxes. So I didn't like this kind of work, but AI really went into that direction in general, so you can't really escape. And so we did things with that as well. I'm going to take the right key here. And in fact, we had quite some success also, because we didn't have to do only that. So this big data era actually offered other possibilities too, with unsupervised and self-supervised learning, which allowed more interesting things. And so we basically did a couple of more industrial commercial things. So Rüdiger mentioned next thing. So this really started with this book, The Art of Deception, which I had somehow as a Christmas gift or something. Anyway, this fellow, Kevin Mitnick, he described social engineering attacks, and so how people managed to break into systems that were completely secured simply by calling up and saying, hey, I'm your coworker, it's Friday afternoon, I have to finish this, I forgot this thing in the office, can you please log me into the system? And we asked ourselves, well, what could be done against that? And we said, well, with analyzing the data, we could actually build patterns of users. So if somebody steals my password, he's not going to use the computer in the same way. And at the time, we tested this with students in the computer room. I mean, completely illegal today. But we basically found that the patterns of usage for 250 accounts or so on were completely different. We could really tell them apart. There was only one false positive or so. And then we said, okay, great, that's like a no-brainer for security. You know, if somebody steals my account, well, he's not going to be able to match my pattern because he doesn't know what it is, and you know, it'll be difficult to do. And so I kind of sponsored the development of a prototype. In the end, it became a spin-off and it became quite successful. Actually, not so much on the security end, but you know, the same kind of idea was tweaked in other directions as well. Another example is a recommender system. So Predigo, we developed a new approach for building product ontologies for recommendation, again, just from buyer behavior, so a kind of unsupervised, the unsupervised learning again. And finally, we also worked on news recommenders with context trees. This is something that ran for quite a long time on Le Point, a big French news site, also on some Swiss news sites. This one didn't turn into a company because we were told that this business operated according to different rules, and it wouldn't be easy to really sell this kind of thing. So we did do quite a number of things like other people. You know, the knowledge-based systems were too expensive. These were things that were more feasible and that actually could make money and could be useful. One element of this data-driven thing was that we usually didn't have enough high-quality data, and certain things that were a little bit out of the ordinary, it was very hard to get data about them, and so the systems could sort of handle the usual cases, but not the edge cases. And so all the large AI companies have big crews that do crowdsourcing. They basically ask questions to people, and they ask people to provide the data. And the difficulty is you want to make sure that they do it truthfully. And the challenge is that workers usually are not diligent. The interesting phenomenon is the more you pay, the less good the answers are because you attract people who only do it for the money. And so you need to find some kind of incentive that actually brings smart people to work on this. And one solution is to, for example, make it a game. And amazingly, you don't have to pay anything. So you can just make people play a game, and you make people provide you with lots of information. So that was another interesting, I think another very interesting approach. And finally, for obtaining the truth, well, you know, in the end, things will come down to money somewhere in the large scale. And so, you know, the crowdsourced information really can be wrong because people don't put in the effort. Maybe they have ulterior motives. They want to change the outcome. And it turns out that if you look at the consistency of the data you get, you can actually separate wrong from right. This kind of technique, though, has some problems with game theory for uninformative equilibria and in handling subjective data. So we did some work on this with a number of students. And in fact, we came up with some pretty nice techniques. So they could also be used for really paying for data and ensuring that only real data actually gets paid. And why is that important? So if you look at, for example, ratings on Amazon, so on the top there, on the left, you find the ratings that you find on Amazon for a certain music CD. This is already quite old, I think from 2006 or so on. But you will find this funny U-shape. So either people really like it or people really hate it. And if you give this same CD, somebody gave it to 60 students, and you get this distribution at the bottom. So this bell curve, which is normally what you expect. So some people like it a lot, but most people like it so-so. And the reason why you get the U-curve is there's a self-selection here, which is that the people who are motivated to go and write reviews are the ones that either get paid for it, or they're friends with the group, or they really like it, or they kind of really hate it, and so they want to get even. But the ones who are not very emotional about it, right, they don't write these reviews. So if you take this distribution and you try to make conclusions from it, like which is the better CD or so on, well, you know, there's a real question of how much significance that has. So you do have to pay for data. If you pay, you know, then you could get a better distribution. And we came up with this technique called the peer truth theorem, in which this was an example down here of sensors. So, one model could be that sensing pollution, you can operate a sensor and you get paid for the data. Okay, and to motivate you to keep your sensor clean, to clean off the bird shit, and to, make sure it really works right, you should be paid only for true data. And so with this scheme, we can actually, this is a simulation of the city of Strasbourg, we can actually really show the payments, the honest ones, they get the blue payments, and if you just report some random data, which doesn't correspond to anything, you get these red payments, and they actually have exactly an average of 0. And so we managed to really have a scheme in which we can pay people for data. We can make sure that only real data will be rewarded. So this is actually this data-focused machine learning. We also worked a bit on natural language, was always a bit of an interest of mine, and so we worked with reviews, recommendations based on reviews, critiquing in text, this example critiquing I showed you. And the problem we had is, I think the ideas were very good, but the language technology was too weak. It was just not exact enough. There were too many obvious mistakes in there that made these things not very credible. And so I think these ideas are good, and I noticed that we get more and more citations of these papers these days, so they are coming back. But in the end, the real weakness of these big data approaches is that you cannot distinguish causality from correlations. So, if you have data, let's say medical data, you might occur that flus and headaches, they often occur together. But that leaves 3 possible causal models, right? One of them is that the flu and the headaches have some other underlying symptom, some other underlying cause, sorry. Another one is that the headache causes the flu, and the third one is that the flu causes the headache. And so it's pretty important if you want to treat these symptoms to know which is the right model, because you may be trying to cure the flu with a painkiller that makes the headache go away, but that's not going to work because it's not the correct model. And you can only learn the right model if you also find data, for example, about a headache without a flu, right? That could rule out this model. And normally, observational data, you're not going to be that lucky that you have all this data, and you need to make some kind of experiments to complement the data. This is what scientists do, right? And but if you just take big data, that's not scientists. That's not collected with a purpose, but it just doesn't let you have this kind of causal information. So that's why I think there's a lot of limitations in this machine learning approach, even though people call it data science and so on, but I think the expectations there are really a bit overdrawn. So let's get to, we're today in the age of large language models. So language models actually are quite old, and I actually heard about those at ETH as well from this fellow here, Jim Massey, because this was actually in the first paper about information theory for Claude Shannon. And this is a little excerpt in there. So he already built a language model. Of course, not a large language model, but a very small language model. But I myself actually was quite interested in that. I thought that was a really interesting idea. And I remember I wrote applications for graduate school. And I said that, you could build these language models, and it looks like really interesting. You might be able to do some reasoning and so on with them. But I was a little bit ahead of my time, I think, and I didn't pursue this. But it is really quite an old idea. And now we have this turn since a few years ago. I think we crossed some kind of threshold where these language models that you can just learn from language, the way Shannon described it, you can use that as a source of common sense knowledge. Because they become really so accurate and so good now that we can actually use them as a source of knowledge. And so this problem with having to formulate knowledge by hand, having to have PhD level graduates that could do this, we could actually get this out of such a language model. And there's a huge difference with the data science, because here we summarize human knowledge, okay? Because everything that goes in our text, and there are scientific papers and things like that, and they include causality as well. And they can do one-shot learning, or what we called explanation-based learning at the time. So they can do a lot of things that are actually more about intelligence and not so much about just simple statistics. But they require a little bit more thought. So, for example, the language models, they do have knowledge of causality, but the knowledge is encoded in the way humans think about causality, which is not the mathematically correct form. Humans, they focus on a single cause and not on the multiple causes, this whole complexity of a causal graph and so on that eludes people. So people have a simpler approximation. And so people have tried to extract these more complex models from language models, and that didn't work. But if you try to actually really use these human-like models, you can actually get very consistent information out of them. So this is an example of a paper that was published last year. So these language models, they really reproduce human weaknesses. Also logical fallacies, they often hallucinate things that are actually logical fallacies. Now, it turns out that you can train these LLMs to recognize logical fallacies. So you present them with a large number, database of logical fallacies. And then you can tell them that, well, they should filter these out, what they recognize. And it's a bit like people. You generate something, then you realize, oh, it's nonsense. I should not say that. And so this actually got us an Outstanding Paper Award just at the NACL conference, the main US conference on computational linguistics. We do have to work with these language models, and we have to take into account that they have the human weaknesses. Now, there's another problem with these language models, is that they kind of pretend to do reasoning. So they can produce sort of chains of thought. For example, this is another example from a paper we published. So you can tell them that the accident rate when traveling by air is 1 in 9,821. When traveling by car, it's 1 in 102. And that 1 divided by 9,821 is less than 1 divided by 102. So hence, traveling by air is safer than traveling by car. So they can come up with that chain of thought and that reasoning. However, if you tell them that the accident rates are different, you say that the accident rate for traveling by air is 1 in 102, and by car it's 1 in 9,821, then they will still say that traveling by air is safer than traveling by car. So they actually don't follow these chains of thoughts. They claim to have this chain of thought, but in reality, this is generated separately, and the LLM just does something else. But this chain of thought has nothing to do with how they actually work. So that makes it a little bit difficult. And when you go to something like planning, remember that was one of the huge successes of AI, then you really go beyond the LLM capabilities. They can solve almost none of the typical benchmark problems that people solve with AI planners. OK, so I'm really kind of out of time. So let's go to the difficult part, the predicting the future. OK? Clearly, since 2022, AI has been sort of defined as being large language models. And I think it's not entirely wrong, because I think that is actually really has interesting knowledge in there. But it leaves little room for other aspects, right? Other aspects of AI. And some famous person has said it's an elephant in the room and it sucks out all the air. So actually, I would like to rephrase that. I would like to say that these other things, they have to adapt to the elephant, okay? They have to kind of smooth themselves and make a deal with the elephant, right? And I think that's the kind of direction that AI should be going. Now, the big question also is always, are large language models a bubble? I think that they're a huge breakthrough, and they can do a lot of things just by themselves, even without using them further for intelligent tasks. So I think, definitely they're not a bubble. I think they're pretty useful for a lot of things. They can translate things and so on. So they're not a bubble. But now I'm going to have a list of things. So the first thing is this weakness of reasoning by chaining. So you can teach them to reason by chaining, and you can actually teach them, for example, how to do resolution theorem proving. You can teach them how to do simple constraint satisfaction. But since the architecture doesn't match, that is, you don't have a good short-term memory, the only short-term memory are these prompts, and they are not evenly accessed. Like the position in the prompt makes the usage very different. You don't have this part, and so you can't scale it to any large problems. They can only solve small problems. You can teach them to solve small problems, but they cannot scale. So we need to invent something so it can actually solve large problems, things that use these particular algorithms. Also, there's this question of artificial intelligence. Artificial intelligence should somehow go beyond what people can do. LLMs can simulate what people can do, but planning, design, complex problems, these aircraft allocation and so on, I don't think the language models can do these very well. And so there's still a lot of room for other kinds of AI that can do that. Another thing is that it has become a bit of a spectator sport because there are only a few large companies. So at the time when we did NextThink, we had 2 people working 18 months to produce a prototype on some Sun workstations, and that became the prototype for something that went up to a $1 billion company. Today, people want to found an AI startup. They first raise $100 million or something to buy huge computers. And so very few people can do that. And the research agenda is so much driven by large corporations, and we can just observe, oh yeah, somebody came out with a new model, and oh, have you tried it yet? But it's not at all the same as what we used to do when we built these models ourselves. We could just go to the lab, and we could have a bright idea, and a year later, it would be a company, right? This is no longer possible. So that's I think, a problem with the current state. There's something also that people forget, which is that these techniques with multi-layer perceptrons, they cannot do continual learning. So we always have to train the model on all data at once. And so the OpenAI has to go back and say, okay, now we're going to run 6 months of all our computers, and we're going to come up with the next model. People can learn continuously. Whereas these networks, whenever you introduce a new task, so this is an example where you have kind of trained it on one task, then you bring in another task, so it starts to learn this one, but it forgets. It becomes less good at the first things, at the things it knew before. So we cannot have a continuous evolution. And that's also a blockage. At some point, we're not going to, already you can see it now, that there's not much progress anymore beyond these GPT-4 models. The GPT-5 is sort of announced but not coming. So that's a fundamental issue. You need different kinds of neural networks to run these things. A lot of people talked about the problem with black box models. Energy consumption, certainly, I think everybody knows it's a little bit ridiculous to build nuclear reactors to run an AI program. I need to say probably something on the impact on society. I'm really not an expert, so I don't want to say a lot about this. I think AI will maybe eliminate taxi drivers at some point, but it also creates job opportunities, right? So the translation, machine translation, for example, somebody who doesn't speak Urdu, he could work with people in Pakistan who don't speak English, right? Or somebody like me who cannot draw can create illustrations like the ones in this talk. And so, it creates more opportunities as well. I wouldn't just say at the beginning that the net has to be negative. There are also these criticisms like AI is unfair and so on. Well, it does amplify human biases because the learned models typically only pick the most likely solution, so it doesn't give the same distributions. But you can adjust it. You can adjust the decisions that analysis to make to whatever fairness criterion you want. Try to do that with people, right? It's impossible. So, that definitely is a way to get a more fair society rather than what we have now. So my take on this is, if we let the lawyers take over and rule out everything, make everything illegal, we'll never know what we've been missing, right? So I would rather, let's try a few more things before we go back. I'm not an expert, so it's just my personal opinion. Okay, let's skip that. I have a lot of PhD students and postdocs, and whatever I've been talking about our work is really their work very much. They spent more time collectively on that than I did. And so, I thank all of them for the work they did, and many of them are actually here. I'm really very touched by that you made the trip. And I'm very happy to have this kind of homecoming. And thank you very much.
Now we get to the official part where we're going to bestow an honorary degree upon you. But for that, we need an important person. We need, in fact, a very important person. And we're lucky, not only do we have a very important person, a VIP, we have also the VPI. And so with great pleasure, Ed, please.
That's a good one, by the way. Never heard it before. So my job is I have a job and a constraint, right? The job is to do something extremely formal, and the constraint, and I'm standing between you and the apéro. But before the formal part, I've always enjoyed going to these honorary lectures whenever there's a colleague that I know that is retiring. Now I also do it as part of my job description to people that I've never met. It's kind of interesting when you go to an honorary lecture of somebody you've never met and you're there to do the job. What is common, whether it's people I know, people I don't know, whether I have a cognitive bias or not, is there is always a sense of warmth in the audience, right? This is a reflection on an extremely well-deserved career, illustrious career, a long career at EPFL, and I think that the people that are in the room are also there to thank you and to also support you in the next phase of your journey, which my personal recommendation is just enjoy it. I mean, I think some colleagues are petrified at the idea of going into retirement. Others are really ready and have many plans, and we haven't had that conversation, but I wish you warmly the best to you and your family in the next chapter of your life. Now, the formal part. So first of all, as Vice President for Innovation of Impact, I'd like to acknowledge the presence and the service of the President of the Commission du Corps Enseignant, who is with us in this room. If you have no idea who that is, it's Volkan in the first row. And thank you, Volkan, for your service. This is actually a very important corps constitutif that actually is part of the machine that actually makes operate EPFL smooth. And actually, it is at the recommendation of the Commission du Corps Enseignant that this degree is awarded. Now, for the formal part, I have to read it. And this is, it's actually fine print. It's really not designed for people of our generation, and you'll probably need your reading glasses to read it too. So, and it's also in French, and one of the rules of the laudatio, of any laudatio, is it's only one sentence, right? So bear with me. L'École Polytechnique Fédérale de Lausanne, sur proposition de la conférence du corps enseignant, décerne le titre de professeur honoraire à Monsieur le professeur Boy Faltings, en reconnaissance pour ses réalisations scientifiques remarquables dans les domaines de l'intelligence artificielle, de la programmation par contrainte, des systèmes multi-agents, du e-commerce, et en particulier pour ses contributions en théorie des jeux computationnels et en intelligence artificielle préservant la vie privée. Point virgule. Pour son engagement constant en facteur de l'excellence académique et de l'innovation, incarné par la direction du laboratoire d'intelligence artificielle de l'EPFL et par l'encadrement de plus de 40 doctorants, point virgule, ainsi que pour son soutien indéfectible à l'entrepreneuriat illustré par la cofondation de 6 entreprises spécialisées en intelligence artificielle et le mentorat de nombreux autres à l'EPFL de 1987 à 2025. Félicitations.